Hello, today I want to talk about the close-up theorem. Okay, a natural question for us is for function f, if the mixed second order partial derivative at z, can we switch the order? Okay, if we switch the order, will the result still be the same? I mean, is fsy always equal to fyx? Let us see an example first lah. Okay, you can see this is an example of function of two variable. Okay, a question is fsy equal to fys? Now let us compute it using the knowledge on calculus 2. We can find fs and fy, and then we can find fsy and fys, and we can see that they are the same. So for this example, we can see that fsy is equal to fyx, and I mean, for this question, if we switch the order of differentiation, the result will still be the same. But actually, this is not always the case, huh? Okay, so let us see the next example. I will show you this is not always the case. So for this function, let us find the mixed second order partial derivative at the point 0, 0. Okay, so using the definition of partial derivative, we can find that this equal to negative h and this equal to h. And now we take the partial derivative again using the definition of second order partial derivative. We can find that fsy at point 0, 0 equal to negative 1 and fys at point 0, 0 equal to 1. So this example tells us that fsy is not equal to fys at point 0, 0. So if we switch the order of differentiation, the result may not be same, may not be equal. So now let us introduce a very powerful theorem called close-up theorem. Okay, if you first time see this theorem, you will feel that this theorem is very hard to understand. But actually, this is not. Okay, very easy. This theorem is very easy to understand. Let's explain to you. This theorem tells us that for a function f, if the second order partial derivative at z and are continuous at point s0, then we can switch the order of differentiation if the result will still be the same. They are equal. Okay, and the proof of this theorem is very long, but the idea of the proof is not very hard actually. So let us go through it. Okay, I will explain the idea. Okay, so the question is about a function of n variable, right? But actually we only focus on two directions. So we can reduce this question to a question of function of two variable using the chains of variable. Okay, and the question will become easy. Okay, so we define a function called guv first. Okay, equal to this. Okay, so this function is well defined because this point actually is in the domain, in this domain. Okay, now I want to show you this equation is true. Okay, this equation is true. So we first take the partial derivative of g with respect to u, and we get this. Okay, and then we take the partial derivative with respect to v, and we get this. Okay, so now we get this result, and using the similar way we can get this result. Okay, and it is not very hard to understand because we just apply the change of variable. So this result is not surprising lah. So this actually means if we take the derivative partial derivative of g with respect to u, okay, is actually same as we take partial derivative of f with respect to si. Okay, it's the same actually because we just using the change of variable. Okay, so now we plug in the 0, 0, 0.00 into these two equations, we'll get this. Okay, now the question is become easy. Okay, the proof become easy because if we prove these two are equal, then we complete this proof. Okay, because it will show these two also equal, complete our proof. So by the assumption, the mixed second order partial derivative of f is continuous and s0. So this implies that the mixed second order partial derivative of g also continuous at point 0, 0. So now we need to show that these equations are true. These two are equal. Okay, so now let us define a function, define this function, and we let SVU equal to this, SUV equal to this. And this function will become this. We can write this function become this, or write this function become this. Okay, now let us feed the variable v as a constant. Okay, so now this will become SVU will become one variable function, and then we take the derivative with respect to u, we will get this. Okay, now let us focus on this equation. Okay, since this is a function of one variable, now we can apply a mean value theorem. We will get this. Okay, and we can plug in the number we get from the mean value theorem into this equation, and we will get this result. Now we can fix the variable u as a constant, and this will become a function of v, and we apply the mean value theorem again, we can get this result. Okay, and using similar way, we can show this result lah. Okay, so now we fix the u as the constant, and this will become a function of one variable again, and we take the derivative, we can get this result, and we focus on the equation. This is the one variable function now, so we using the mean value theorem, we get this, we plug in here, and in the similar way we can get this result, and we fix the v as a constant, and now this is become a function of u, and we apply the mean value theorem again, we get this. Okay, so as you can see, this and this are the same equation, so we can get this result lah. So now the question become easy. We can take the limit on both sides. Okay, take the limit on both sides as uv approaches to 0, 0, uv approaches to 0, 0. Okay, so as uv approaches to 0, 0, these two will converge to 0, 0. So since GUV and GVU is continuous at 0.00 by our assumption, so these two will be equal. Okay, so now actually we already complete our proof, because we already show that these two are equal, these two are equal. So if this equal, so we will get this result. Okay, so you can see that the proof is very long, right? But the idea is very easy to understand. Let me explain again. So we only use the chain of variable, and then we fix one variable as a constant, and the function will become a function of one variable, and we apply a mean value theorem again and again. Okay, and then we can solve this question. So the idea actually is very easy, not too hard. Okay, so this is the proof lah. Okay, now let us see an example. Okay, this is an example. This is example 2. Okay, and for example 2, when sy is not equal to 0, 0, let us compute the fsy and fys. We can see that fsy and fys is equal to this, and this is a rational function, and we know that a rational function is continuous. So the fsy and fys when s not equal to 0, 0 should be the same. Okay, and we can see that this is the case. Okay, this is the case. And now let us see another example. Okay, so for this question, this question have two function. Okay, and this two function have a first order partial derivative, and the first order partial derivative is continuous on R2, and we have another function called f, and we have del f, del x is equal to this, and del f, del y equal to this. We want to show this equation is true. Okay, actually this question is very easy, because if we take the partial derivative both sides, okay, both sides, we can get this result. And by our assumption, this is continuous, this is continuous, so this is continuous. And by the cross-swap theorem, this will equal and this will equal. So this complete our this example lah. Okay, so in conclusion, the closed-loop theorem is a very powerful theorem. It gives us a sufficient condition for the equality of mixed partial derivative. But without the continuity assumption, we cannot say the fsy is equal to fyx or fsy is not equal to fyx. Okay, if without the continuity assumption, we cannot say something lah. Okay. And the closed-loop theorem tells us that for a function, if the mixed second order partial derivative essay and continuous at the point, we can switch the order of differentiation. So the continuity assumption is allow us to switch the order of differentiation. So this is the closed-loop theorem. Okay, so this is the reference. Thank you.